Good afternoon, everyone, or good morning, or good evening, depending on where you are in the world. I want to start by giving my sincerest gratitude to Stuart Wilson at BrightTALK and also the community itself for offering me the opportunity to host this webinar. It really is an honor and a great pleasure. My name is Jacob. I'm the IT Director at Phoenix IS/IT Corporation in Memphis, Tennessee. Part of my everyday job is to manage the division that provides MSP services to our business and corporate customers in the Mid-South. I have about 8 years of combined background in IT and IS-related industries. I've worked in systems administration, network engineering, and wireless communications. And in the past 4 years, I've been sort of more focused on offensive security and cybersecurity topics. I also have a combined background in RF and signal processing, which has been a lifelong passion of mine. I love the physics and characteristics of RF, so I am a big Marconi fan. I'm a licensed Class A ham operator as well, so I do spend a lot of my time researching various RF technologies, especially in the 802.11 domain, but also in other industrial and commercial technologies, such as LoRaWAN, SDR, Bluetooth, and obviously the BGP cellular standards. So I guess I've kind of naturally combined my RF passion with my background in IT, so to say. Today's webinar is going to involve the hot topic of 5G transformation and the implications it'll have on our society from a security-centric perspective. So let's start off by talking about what the definition of 5G actually is, because it's really not just another G to add to the generational evolution of cellular communication systems, so to say. The 5G standard is a fundamental approach to realize the vision of an all-connected society, ranging from industrial, societal, transportation, government, healthcare, and residential services, which will all form a communications web of always available, ultra-fast connectivity with real-time response. It's deemed as a service-based architecture. It's really a major milestone in realizing the next generation society, so to say, right? Where everything that would benefit from it has a unique communicable address to literally be reached anytime from anywhere. So it's kind of fair to deem 5G as an industrial revolution. So before we head on, I think it's important that we just look at how the evolutional progress on cellular technologies have played out since their commercial advent, just to kind of get a better picture of the security efforts that has sort of progressed along evolution. So let's get the slide up here. See the chart here starting from the 80s. So the 1G cellular standard dates back to the early 80s. And at that time, we had a wide array of disparate and incompatible cellular technologies deployed across the world. In the US, we had AMPS, northern parts of Europe, we had NNT. We also had the TAC system in Germany and UK, also called Total Access Communication Systems. And there was even earlier attempts to standardize the cellular communication infrastructure, and those technologies are often referred to as 0G or pre-1G technologies. But they were crude and not practically implemented, so they never really saw a global scale, right? But the common denominator for all 1G standards is that they were analog in their fashion. So communication between user devices and the network took place in the clear without any form of encryption to safeguard the privacy and security of end users. So back then, it was fairly easy for threat actors to sort of utilize off-the-shelf RF equipment to conduct passive and active attacks on the infrastructure or eavesdropping. So now this majorly diminished in the earlies when the second generation cellular network, or 2G as we know it, was introduced. In Europe, we saw a mass-scale deployment of the GSM standard, while in the US, we opted for a digital version of AMPS, which later enhanced to the IS-95 system, and some operators were heading for CDMA technologies. So with these standards, we now had a radio access network operating in the digital domain, so to say. We introduced the use of universal SIM cards to form integrity, and as well as encryption of the voice data itself. And although the core network was still very much a circuit switch network, the approach of introducing encryption between base stations and user equipment made it extremely difficult to conduct passive eavesdropping. So the 2G system really set the foundation of securing communications between users and the network. And we do have to admit that although the fairly weak A51 or A52 cipher used in the GSM standard, for example, has been broken using modern technology, considering the age of the standard, we've done a pretty good job following the evolution of security requirements. And so most innovations to realize packet-based radio access took place during the introduction of 3G. with systems like UMTS or CDMA 2000. So the 3GPP was formed, and they worked together with ETSI, IAT, and large established telco providers to form the third-generation security standards for the radio and the core network. And those standards were actually later on brought in as the baseline for 4G security as well. So we introduced new encryption algorithms and authentication methods that to guarantee confidentiality and privacy and security for users connected to the cellular network. And this obviously raised the security bar to a whole new level. So, and honestly, I would love to dive deeper into the actual improvements from an RF and security perspective between each standard, but that's not really what this webinar is centered about, because we are going to talk 5G here today, I promise. But the technical complexity around the evolution between cellular standards is just astonishing and really deserves a deeper discussion. But another time, right? So it's also worth noting that during the rollout of 3G, right, there was a similar skepticism regarding the security aspect of deploying a whole new concept of communication as what we're now seeing with 5G. So when we moved from 2G to 3G, we went from relying on a circuit switch traditional network architecture with low-speed data capabilities to a high-speed network that brought the ecosystem closer to becoming IP native, so to say, right? And although being embraced for all the potentials and benefits that comes with such a big leap in communications technology, we as a society had no previous experience in dealing with such a capable technology that now introduced mobile broadband, video calling features, and multimedia streaming services. So we kind of felt uneasy expanding our traditional hardwired internet to desktop fashion to an all-mobile platform. And this in turn obviously sparked the need for being able to access everything from anywhere. So as with the general industry concerns on the topics of 5G, although not to the same extent, right, we did have similar concerns with the introduction of 3G back in the days. However, we did overcome the major security flaws back then, and I think it's important to bring that to the general discussion on 5G, even though, again, the criteria for 5G are far greater and more complex. So simply put, with the later introduction of 4G or LTE, for data access, we went all in and ditched the circuit switch network, the core networking, and replaced it for an all IP-based packet switch network. Let's see here if the slide updated. There we go. Okay. We also introduced new RF and radio access technologies that enabled more users to be connected to the network at the same time, with a much higher data rate than previously possible, obviously. So now with the technological criteria defined for 4G, especially in the later revisions, we had as a society started to realize the massive potentials in having a fully orchestrated packet-based network. So although the concept of IoT and MMC, like LTE-M and NB-IoT, has already been a part of 4G for a while now, with 5G, RF technology, network technology, and most importantly, computing resources have all evolved to a point where it's sort of practical and financially viable to enable mass-scale connectivity and to introduce critical industry-grade IoT technologies. So obviously, in comes the 5th generation cellular standard. Again, unlike previous cellular technologies, the 5G standard is not just about upgrading the telco infrastructure to allow for more clients and higher data. It really is a new concept of communication, right? Based on inherently on software-defined models that enables technological possibilities previously deemed too costly and too complex to implement in practice. So the core network is now completely softwareized in essence, which permits a level of scalability, agility, and performance that stretches current communication standards way beyond 4G. So not just including improvements on the RF side of things like massive MIMO and beamforming capabilities, these technological advances are indirectly due to key improvements in the network domain. So traditional core networks have generally been based on vendor-defined hardware and software with fixed-purpose appliances, so to say. And so in simple terms, 5G reaps benefits from NFV, or network function virtualization, that separates a defined networking function from its underlying physical plane and runs it as a virtual instance on a commodity server. So these instances can be configured, enhanced, added, or removed in real time on demand to accommodate scaling, resource needs, and user requirements. It combines these functions by operating the stack over a software-defined network, which separates the control plane from the data forwarding plane. Very similar to the concept of SD-WAN technologies, which many large enterprises have already undertaken. And this permits for centralized access, configuration, and third-party integration over the entire network infrastructure. So this approach aligns the network with cloud services from edge to core, which brings processing resources closer to the end user itself. So in essence, the traditional architecture is now virtualized, which allows the infrastructure to adapt to constantly changing variables faster than ever before. And it also obviously lowers overall CapEx and OpEx. It's significantly more affordable to run services and function as software-based functions, right? So SDN and NFV are both underlying technologies, fundamental to the criteria and enormous expectations of 5G. And on the topic, it's also worth noting that the current revision of the 4G standard also already have some SDN and NFV implemented in the core network already. So we have virtualized networking functions already in the 4G network, but not to the extent and requirements of 5G. But again, we've been deploying virtualization on commercial networks for some time now already. So these technologies are not inherently all new. The 5G infrastructure operates in segmented network slices that may be seen as a way to provide isolated subnetworks. And each of these subnetworks are optimized for specific types of traffic. So in essence, QoS, or quality of service, is now inherently a part of 5G by assigning certain types of devices and capillary networks to different slices, right? Where each slice is optimized for a specific application purpose. So in other words, one slice may be dedicated to massive IoT, one for critical IoT, one for mobile broadband, and another for V2X, for example. So each slice is optimized to provide a certain response time, resilience, and throughput, and also security that's required by specific use. Now, this is a very, very complex setup that requires orchestrators to work in tandem with SDN controllers and the radio access network in real time. So the back end of things is really highly complex in logic, right? But it's simplified from an administrative perspective. But however, due to the approach of slicing the network in different subsets of access and performance requirements, security aspects aside, we're now able to enact SLAs and ELAs, like service level agreements, that were previously only feasible in legacy networks, and maybe not so much in the cellular domain, right? And this in turn opens up the possibilities of using 5G for critical services. So we are going to see slices optimized for entire smart city purposes to monitor and control sensors for electrical grids, traffic management, and other critical signaling, and which will all require ultra-fast response times, right? And the same goes for V2X, or vehicles to anything, where sensors between vehicles and autonomous cars will require instantaneous response times in order to provide safety-related services. So to sum it up, the drivers behind previous mobile network evolutions have predominantly been about increasing throughput and reducing latency, right? And security drivers have remained in place to provide a trustworthy connectivity service. And this type of trust will continue to be a driver for 5G. But since 5G will be designed to serve entire industries and not just legacy end users, the concept of terminal and device will change, and we'll have unattended machines and sensors and robots, so to say, connected as capillary networks involving hundreds, if not thousands, of individual devices. So since the network will need to serve a whole new category of users, the generic trust model will change, and which will create additional requirements in key areas, such as authentication and accountability. And this is to address IoT devices that are typically unable to comply with current security standards or legacy security standards, which introduces a whole new attack surface itself. So it's possible that we'll see a whole new concept of DDoS attacks, for example, that will surface and that could possibly cause severe service outages across entire industries and cities, and obviously which could have detrimental effects on public safety. But so with the introduction of large-scale device connectivity across multiple industrial sectors, you're naturally expanding the potential attack surface of the network. So I think it's important to stress the fact that the societal and industrial transformation to 5G is the primary concern when it comes to security itself. and not necessarily just in the technological domain, because we're so focused on the technological limitations of defending the infrastructure, right? But the 5G standard actually employs stronger overall security on the ecosystem than previous generation standards. So it's more the fact that we're stretching the concept of what can be reached over IP. We're sort of digitizing the society to far greater lengths than ever before. And as such, security naturally becomes a greater concern since the impact of an attack may now have a more detrimental effect. And I think that personally that the predominant challenge of preventing attacks will be kind of compounded by IoT deployments in situations where there's an absence or a lack of technical expertise, like small businesses and residential homes. So this is something that we're already seeing in the industry, right? Where hackers have compromised lighting control, thermostats, cameras, and other common gadgets seen in these typical scenarios. So from a malicious standpoint, we are going to see the use of mass scanners and IoT harvesting tools as the norm for hackers looking for vulnerable endpoints. And also, general concerns on user privacy in the society has also increased dramatically over the past 5 to 10 years. And this is an issue that becomes even more focused on with developments in big data analytics permitted by 5G. There's going to be a drastic increase in the amount of telemetric data collected from a wide range of connected sources. And this in turn will require certain regulatory guidelines on storage and access to comply with privacy laws. So what characterizes 5G even more than previous cellular standards is that it will have a crucial role in the operation of society. And so naturally, the full scope of privacy will be a concern that really spans beyond technology itself, and will eventually impact legal frameworks and actions by entities and individuals. So we'll absolutely see increased regulatory involvement in how entire 5G infrastructures will operate as the standard matures over time. But again, going back to the concept of network slicing, the segmentation itself, or the slicing, could be seen as a part of security and safety requirements. Operators will need to ensure a properly implemented isolation model to support slicing in order to confine the impact of security requirements to single slices rather than enable it over the entire network. Because different industries and different sectors and user cases will require different form of security profiles, so to say, right? So the typical approach could be to specify a number of standardized security enables to be present in all slices as a baseline. Then on top of that, application-specific security definitions could be enabled. So by running properly operating virtualization layers, external entities such as enterprises could securely deploy their own software inside a 5G network, and this will sort of act as a governance to organizations utilizing 5G. And as I discussed briefly earlier as well, since 5G will inherently rely on cloud and virtualization services, since it's a software-based architecture, right, there'll be a solid dependency on secure software code. So let's go over to the next slide here. Until now, dedicated and often proprietary hardware has been used to interconnect functional nodes and interfaces in the typical network, right? And now, by separating software and hardware, telco software can no longer rely on specific security attributes of a dedicated telco hardware platform. And this is a topic that will obviously require an open communication between developers, vendors, security, and IT personnel, where, say, vendors offering proprietary solutions will need to include third-party entities, and maybe even competing entities, in ongoing conversations to establish initiatives for interoperability and security, especially since open source-based implementations have already started to play a role in current cellular standards. And since the network core in 5G will be based on SDN and NFV, we will also be turning to AI technology to provide the necessary functions to render the network intelligent enough to cope with constant changes on the user plane, network congestion, and also for major security needs. And another part is that when it comes to security itself, I think it's important to keep in mind that trying to address all possible requirements of every stakeholder in the same network could lead to a reduced security level, or maybe even to a solution with cluttered security guidelines. So it's sort of required that a well-designed and flexible security baseline is established amongst everyone, all stakeholders, from operators to vendors, regulators, and policymakers. So we also need to highlight the fact that although 5G is designed to be a platform for a wide range of user groups, some of them all new user groups, it doesn't really inherently mean that it's necessary for the 5G network itself to carry the burden of all security responsibilities. The 5G infrastructure may guarantee that payloads are safe when traveling across the network, right? But once it reaches the termination point to, say, the public internet, it's up to the application or service used to maintain security and confidentiality. So another concern is that, which is a little bit off the topic here, but it goes into the radio security. Another concern is that we need to consider the aspect of base station security in the framework, really more so than in previous cellular standards. SDR, or software-defined radio technology, have progressed drastically the past 10 years. And as computing resources are becoming more affordable, obviously, the practicality and affordability of wideband SDR hardware has followed along, right? So, and this may render possibilities of malicious use. So there will be a need to enforce radio network security to resist potential attack vectors in this domain as well, which follows the technological evolution of similar technologies such as SDR, especially since 5G will permit dense deployments of many small radio cells with a obviously very saturated landscape of connected users and IoT devices. And this, in theory, makes it easier for threat actors to discover vulnerable entry points into the network. And again, due to the good isolation properties within 5G, it may be challenging for a threat actor to target the core network itself. But since a lot of the processing is now being placed at the edge in 5G, there's again a risk that localized radio attacks, again, using SDR hardware that is readily available off the shelf, may cause service degradation or even interruption on potentially critical services. But I really think that it's important to emphasize on the fact that the aspect of security itself goes beyond technological capabilities. And instead, it may be looked at as a way of coping with societal and industrial expectations of available technology, no matter the platform or the systems running it, right? So 5G is designed and expected to work with a wide range of applications. And so, I mean, naturally, the complexity of operating the infrastructure is one of the major challenges to address itself. 5G is a platform that makes it possible for service providers to innovate and create new value for enterprises and societies. And with IoT solutions, it will play an important role in everyday business and critical applications. And as I briefly touched on earlier, due to the massive influx of data rendered by billions of connected devices, from a security standpoint, we will have to start relying on AI, machine learning, and automation tools to provide the necessary means for efficient security analytics from edge to core. So it typically drills down to common sense logic, right? Like it does with most security questions, even in the legacy internet domain, where we need to encourage a continued development of trusted 5G technologies, services, and products, where developers need to adhere to, say, DevSecOps procedures to include security as a part of development and not necessarily as an afterthought, right? We have to remember that secure code is good code. We also need to promote trusted development of future generations of communication technologies and enforce international standards and processes that are in nature open and transparent. Also more important than ever before, government and private sectors need to engage in collaborative efforts on risk identification and mitigation efforts on known and unknown vulnerabilities. And this is also to prohibit legacy vulnerabilities from migrating into 5G, like what we've seen in previous standards. For example, with the case of IMSI encryption that we're now introducing in 5G, that used to be a major problem in the previous standards. So as open virtualization technology becomes the standard, right, it won't be long until we stop deploying fixed purpose appliances in the enterprise and in the industrial domain altogether. Again, many large enterprises have already adopted a software-defined network architecture. And the concept of softwareizing communication platforms, again, like SD-WAN, for example, have already enabled organizations and service providers the necessary means of delivering application-aware networks that are intelligent, agile, and decentralized. And this is a crucial stepping stone in realizing a virtualized generation of interconnected industries and societies. So I think we can agree on the fact that 5G is an ecosystem that must be protected as a whole. the supply chain that runs the gamut ranges from radio networks to integrated chipsets and devices, which again are not just phones with 5G, but also billions of IoT devices. And each of these devices have their own component part supply chain, which obviously also introduces risk. And again, this is combined with the risks of the services that operate the now virtualized network itself. But it's important to emphasize that with so many stakeholders actively working on the softwareized communications evolution that we have going on right now, we'll have ongoing research and actions taken on risk management and vulnerabilities across the ecosystem. And so by defining security as a vital component in every step of the chain, is going to be absolute key in order to provide a safe and efficient future of 5G and beyond. That was the presentation out here. And, let's see here. Yes, I'm welcoming questions from the audience here. And I should have mentioned that in the beginning as well, but questions will be answered by the end of the webinar here. That's how I planned it. So let's see here. You mentioned SDR technology being a potential threat to the 5G infrastructure. What would be a use case for malicious SDR? Well, so SDR is a technology that enables off-the-shelf hardware to operate as a radio oscillator across a very broad range of RF spectrum, right? So right now in the market, there are many devices that have the capability to transmit and receive radio signals from very low frequencies up to very high frequencies, surpassing the millimeter bands that we're seeing in 5G. So if you have hardware that are that capable and have the capability of transmitting on those frequencies, you could create malicious jammers or rogue base stations, for example. We already seen similar concepts in previous cellular technologies where rogue base stations have been created with SDR technology to trick users into connecting to a base station that's really that's malicious. So we have some new safeguards against that in the 5G infrastructure, where say if an ongoing jamming attack is going on a base station, the 5G network can shut down that base station and prohibit the attack from escalating into the core, and also fail over to a different redundant base station, so to say. But SDR is a technology that's constantly evolving, obviously, along with the whole softwareized evolution. So we will see more capable devices in the SDR domain as well. And the more powerful they get, the more of a threat they could potentially be. So, and again, they're very, very available and very affordable. And it's usually up to the end user and the programmer, or in this case, the hacker, that utilizes these SDR devices for malicious purposes to program them to conduct certain commands to attack the network. And there we go. In the US, AT&T launched a service called 5G Evolution. Is that regarded as true 5G? Okay. Well, no. Yes and no. So in 5G, there are two ways to deploy the network. There's one way called non-standalone and one way called standalone. So the standalone mode is obviously a full-fledged 5G network, right, where you have all the softwareized functions that comes with the 5G ecosystem, and you have the radio access based on 5G as well. So in a non-standalone mode, which is also what AT&T brands as 5G Evolution, the radio interface is 5G based. So users that have 5G enabled equipment can connect to the network with a 5G radio, right? But the whole infrastructure and hardware and the platform on the operator network is still 4G based. It's still based on evolved packet core, as it's called in 4G. So by doing that, the only real benefit that you're seeing is increased speed, potentially, right? Because you're now having a radio interface that can support higher speeds. But more than that, it's really more of a marketing term that AT&T pulled out. And obviously, they received a lot of skepticism at that time as well for branding their services that way. But so to answer that question, yes and no. There's actually the 3GPP standard allows for a dual operating mode where operators that hasn't fully migrated over to 5G just yet with the whole infrastructure can still enable 5G radio services to end users. So mark that down. Can have time for one more here. What are the major combating tools or properties for defending against threats in 5G? Yeah, that's a good question, right? since the 5G network is obviously almost completely IP-based, the only thing that's not IP-based is the radio interface, right? Because that's in the analog domain still, right? It's radio waves. But the back end of things is all IP-based. The whole framework is IP-based. So pretty much any threat or any vulnerability that goes in the domain of, say, internet or any IP-based vulnerability could be seen as a potential vulnerability in the 5G domain as well. You will have DDoS attacks, different type of hijacks going on, and there will be users trying to reroute traffic within the network. But the major benefit we have with 5G is that we can deploy IDS and IPS hardware within the network. And since we are we will be using a lot of automation and artificial intelligence, we'll have the tools available for us to sort of analyze the network in real time, just like in a legacy network infrastructure and an enterprise, for example. We have the possibility to analyze the traffic in real time to see if there's an ongoing threat. And the 5G ecosystem itself is very scalable, and it's excellently designed to shield off parts of the network that are under an active attack, for example. So if the 5G network senses an attack on a southbound interface somewhere to a node, to a local node somewhere, the network can shut off or isolate the core network from that node itself to prohibit lateral movement within the network. So again, it's a very flexible and elastic design that enables instantaneous reactions and actions to be taken on ongoing threats. But again, pretty much any threat that is IP-based could potentially be applied in the 5G domain as well. I'm sure there's a lot more to discuss on that, definitely, but an IP-based infrastructure is obviously as vulnerable as any other IP-based infrastructure. So there we go. And yes, I'm up to 32 minutes. Those are some major questions I had here. And that's all from me. I hope you enjoyed the presentation and the webinar. This was my first presentation on BrightTALK. I hope you enjoyed it. And I'll hope to see you guys and have you attend one of my upcoming webinars. Thank you so much and have a good day.